This is the chapter that's not a chapter in the book. It's right after chapter 18 and before chapter 19, so I'm calling it chapter 18 and 3/4. This is a preview or an overview of carbonyl compounds. And before we look at the carbonyls themselves, we kind of need to get a feeling for where we are in the grand scheme of things in terms of the redox level. And I've shown you this before, and you can also see this kind of information in chapter 10. Toward the end of chapter 10, they had some stuff about the redox levels of carbon. And so just looking at a progression from the alkane state of carbon to CO2, this is the most reduced form of carbon. And so if you do the little calculation on the redox level of the carbon, you get that carbon is -4 in methane. And if you do the same thing for the carbon in CO2, it's +4. And those numbers fit with where carbon lies in the periodic table, to either need to gain or lose 4 electrons to get to an inert gas configuration. Well, as we progress through, if we start putting in oxygen, just putting in one oxygen and not changing the hybridization of the carbon, then when you do the same calculation, you get that carbon goes to a -2, and this would be true if you put in oxygen, nitrogen, halogen, or the carbon and alkenes are all at this level. If you then oxidize the carbon, and now you're changing the hybridization state of the carbon to go to a carbonyl, but you still have kind of the max amount of hydrogen you could have in there, then it goes to officially a redox level of 0. Now, that is one thing that might bother you a little bit about that, is that, when you look at an elemental carbon or elemental whatever atoms on the periodic table, we say that their official oxidation level is 0. So you might not like this, 0 for this. Also, if you have carbon attached to this carbonyl, then it's still not quite exactly the same, but it's still officially kind of in the middle of the redox scheme. And also for alkynes. So you've gone through more oxidation as you go to these kinds of molecules. Well, if you then replace one of these hydrogens or carbons with an oxygen, then you're further oxidizing the carbon, and so its official oxidation state goes to +2. And this is true for not only carboxylic acids, but also their derivatives, which we will be studying as we go along. You'll see that. It's really important to realize that the carbonyls in carboxylic acids and their derivatives are not at the same redox level as carbonyls in aldehydes and ketones. And so some of their behavior is going to be different. So here's an overview of all these different compounds that contain carbonyls. Excuse me. And so here's the aldehydes and ketones. So by looking, we've said this before, by looking not just at the carbonyl, but also what's directly attached to the carbonyl, that tells you what functional group you have. And so we've got the aldehydes and ketones, and so they are at approximately the same redox level. And then we have all these other things. And all these other things, the carbonyl is approximately at the +2 oxidation state. And so the carboxylic acids themselves, and then all these other things are their derivatives. So acyl halides, anhydrides, esters, amides, and some of these other things we won't see so much of, but things like the acyl phosphates and the thioesters are important biologically. And then a lactone is just a cyclic ester, and a lactam is just a cyclic amide. We really won't have too much to say about those. And most of our nomenclature things are going to be over the main ones, which are carboxylic acids, acyl halides, anhydrides, esters, and amides. So the carbonyl itself, we need to refresh on what we mean by this. The carbon and the oxygen, also the 2 unshared pairs of electrons on the oxygen, and whatever is immediately attached to the carbon at the other end, are all in the same plane. And then we have the pi bond above and below the plane of all of that. And so we know that these bonds are polar, so you might see drawn in some information partial positive, partial negative to help indicate that the bond is polar. And the implication there is that the carbon could act as a Lewis acid. In other words, it could accept a pair of electrons from some other group, and because this bond is polarized toward the oxygen, then the oxygen could then gain control, full control over that pair of electrons. Conversely, because you have these unshared pairs of electrons on the oxygen and this negative character, it could act as a Lewis base and donate that pair of electrons or one of those pairs to some other group. So whether the compound that you're studying behaves as an acid or as a base depends on what it's interacting with. But this characteristic of the carbonyl is important to keep in mind as you go through looking at the possibilities. Now, the way that the book is organized, after this section of the book, we're going to start in on aldehydes and ketones, and the kind of reaction that they typically do is called nucleophilic acyl addition reactions. And so that means that we're going to be adding something. And I mentioned the polarized carbonyl, and so we're going to have the nucleophile react with this partial positive end of the molecule. And by the way, let's go back to the previous slide for a second and think about this drawing is kind of convenient because we kind of see that it's coming in here and we'll go on from there. But if you look back at this picture, really that nucleophile, if it's going to approach this carbon, it's going to have to come in from the top or from the bottom. It's never really coming in from this end because you're starting to make a bond, and making of bonds requires overlapping of orbitals, and so this pi bond orbital is where the overlap can take place. So that's going to be important when we talk about the stereochemical information that we get or we expect as we go through a reaction on that carbonyl carbon. Occasionally that's important to remember that you could approach from the top or the bottom, because then you could get a racemic mixture out of that reaction. Okay, so you have kind of these two choices. If you have a nucleophile, which NU is my abbreviation for a nucleophile, if the nucleophile that you put in here is not a negatively charged species, in other words, it's just an okay nucleophile, then we're going to have acid catalysis to help us out. And so that's the blue route. And so it's going to actually start by this pair of electrons picking up the proton. You get this resonance stabilized intermediate, and then the nucleophile is really better able to deal with a full positive charge on the carbon, and then you finish with addition. So you've added the nucleophile and a hydrogen across the carbonyl. On the other hand, if the nucleophile has a real negative charge, then it'll just go ahead and react with the partial positive character of the carbonyl. And as soon as you start making the extra bond to the carbon, that's going to push these electrons on up to the oxygen, and so you get your tetrahedral intermediate here, and then it can pick up a proton from the other material in the solution. So you end up at the same place, so you've again added the nucleophile and the hydrogen across that double bond. So either way, you're getting the same result. And this is going to happen in the case of aldehydes and ketones, because whatever this Y group is not a good Levy group. So your Y choices for aldehydes was hydrogen, and for ketones was another chunk of carbon. And most of the time, those things don't really want to leave because you've got strong bonds between carbons and hydrogens, and carbons, and so you just end up at this stage for a number of aldehyde and ketone type reactions. Occasionally, they will go on beyond that, and we'll talk about the details in those steps as we get to them later in the chapters. But what can happen is that instead of staying at this addition product, it can go through a couple more steps and end up with a double bond to whoever the nucleophile was. So you started with a carbonyl, you end up with a carbon that's again sp2 hybridized, but now the double bond is to whoever this nucleophile is, and what you end up losing is the oxygen. And so this is a different result because essentially you're doing a kind of substitution, but you're doing it really through an addition followed by an elimination, and and that's different than the ones that we're going to see on the next slide, which involve carboxylic acid derivatives. We'll see a few examples of this, and so you'll have to just learn for aldehydes and ketones which nucleophile families go this route on beyond the addition product and which ones just stop at the addition product. So here's the other option, nucleophilic substitution reactions, which is typical of carboxylic acid derivatives. So in that case, Y is a halogen or another carboxylate group, or an amide, that would be a nitrogen group, or esters, it would be an oxide group, and so on. So once you learn about the carboxylic acid derivatives, not carboxylic acids themselves, they don't do this, but the derivatives can do this kind of reaction. So the nucleophile, again, is attracted to the positive character of the carbonyl, and these guys actually don't need any catalysis because of the nature of the Y groups makes this carbonyl have a lot more positive character than it did in the aldehydes and ketones. And remember, it's in a different oxidation state. And so you'll get to your tetrahedral intermediate, and now this pair of electrons can push that Y group off because these Y groups are relatively much better at leaving than hydrogens and carbons were in the case of aldehydes and ketones. And so you end up substituting the nucleophile for whatever this Y group is. And so there's really not a lot of variation in the outcomes. It's not complicated by something else as it was in the aldehydes and ketones case. So there's another family of reactions that we're going to see that involve reactions at the alpha position of the carbonyl compounds. We won't see that until chapter 22. There's a little bit more information about that in this section of the book, which I'm not going to go into a lot of detail about right now. But the alpha position is the position that's next to the carbonyl, and so the carbonyl is involved in these reactions, and they wouldn't happen if the carbonyl weren't there. And so we can do substitutions at the alpha position and some additions involving the alpha position. And we'll see all of that when we get into chapters 22 and 23. And be able to build bigger molecules and different kinds of molecules, introducing things at that alpha position. So what is the point of this section? The whole point of this section of the book is it's an overview, and so it's good as a reference place. So when you go through your study of carbonyl compounds in chapter 19 and 20 and so on, you're going to kind of need an anchor point. And so if you kind of want to refresh yourself on kind of how these things all relate to each other, then you can come back to this material. And there's a lot of reactions. I mean, there's really a lot of reactions, and yet there's not a lot of patterns. So we had the two basic patterns of substitution and addition, and with addition sometimes we go on, but okay, so you have three patterns of reactions over and over again. Even when we get into chapters 22 and 23, we're really not adding a lot of patterns of reactions. So if you work with me on how we look at the kind of the overview of each type of thing, it really will simplify the whole story into something that's not too complicated. And that is the end of this section of material.